Hi everyone and welcome back. So we're continuing our discussion of nonlinear systems today, first order nonlinear systems, by talking about equilibrium solutions. So let's begin with an autonomous system, y prime equals f of y. An equilibrium solution is a constant vector, y sub e in this case, you can call it anything you like, that solves the differential equation. So any constant solution is an equilibrium, right? The idea is that if it's a constant solution, that's some values for all of the variables involved, all the dependent variables that don't change with time. That's what it means to be at equilibrium, right? No dynamics, nothing shifting, just constant. So we define equilibrium in that way. Now, if you had a constant solution and you put it into the differential equation that it supposedly satisfies, then of course its derivative would be zero. So that means that you're going to have an equilibrium solution if and only if f of ye equals zero, right? So that's the condition we're going to need to use to find equilibria. And that's it. That's what an equilibrium is. So let's just try it. Let's try and find some equilibria. So you'll recognize this system as the pendulum system that we ended the last lecture on. So let's see if this has any equilibria. All we need to do to find equilibria is set the equations individually equal to zero and find a simultaneous solution. We need some collection of numbers for y1, y2, and so on, constants, right? Remember, that has to be constant, that solve all of the equations simultaneously. So what are these equations we need to solve? In this case, we need y2 equals 0, right, from f1 here, and we need minus g over L sine of y1 equals 0. Okay, so where does that get us? Well, we know that y2 is equal to 0, so that's a start. And then for y1, well, we get from here that sine of y1 has to equal 0, and that means that y has to be equal to some multiple of pi, where m is any integer. And so our equilibria, we have infinitely many of them. They are m times pi 0 for m in the integers, right? So our equilibria would be 0, 0, pi 0, 2 pi 0, 3 pi 0, and so on, negative pi 0, negative 2 pi 0, negative 3 pi 0, and so on. Does that make sense? Well, this is a pendulum. The angle, we're talking angles in radians, so if you got an even number of pi, you would have, that would be like 0, 2 pi, 4 pi, negative 2 pi. Those are all situations where, given the system that we have, where the pendulum is hanging straight down, right, equivalent to an angle of 0. And then the other ones, pi, plus or minus 3 pi, plus or minus 5 pi, all the odd multiples of pi would be equivalent to the pendulum sticking straight up in the air. And those are both equilibrium solutions, although they behave differently if they get disturbed a little bit. Sometimes, if it's at the top and you disturb it a little bit, it's going to fall. If it's at the bottom and you disturb it a little bit, it's going to just stay pretty close to where it was to begin with. We're going to be getting into that idea of stability in the near future. All right, so that's an example. Let's try another. All right, so in this case, we have a system. So instead of calling them y1 and y2 in this case, our variables are called x and y. And we want to find all equilibria of this system. X prime equals y times x plus 3, and y prime equals x minus 1 times y minus 2. All right, so what do we need to do? Well, we just need to set each of these equations equal to 0. So y times x plus 3 is equal to 0, and x minus 1 times y minus 2 is equal to 0. Now, just a word of caution here. Never divide by anything, because when you divide through by things, and other than constants are fine, but when you divide through by a variable, it's very possible that you're losing solutions. So for example, in this first equation, if I said, oh, well, I'll just divide both sides by y, I would be missing the fact that y equals 0 is a solution of that equation. And I need that if I want to find all of the equilibria. And it's very important that we find all of them and not miss any, or it will mess everything up down the road. So from these two equations that we need to solve, the first one is solved when either y is equal to 0 or x is equal to minus 3, right? We're just factoring that we're dealing with here, right? And the second one is solved if x is equal to 1 or y is equal to 2. Now remember, in order to solve this, we need a simultaneous solution of both equations. So we need one of the first things to happen and one of the second things to happen. So we have to be very careful about how we put these things together. So for example, we could have y equals 0 and x equals 1. That would give us an equilibrium solution of 1, 0, right? We could say, oh, well, I will have y equals 0, and from the second equation, y equals 2. That's a contradiction. So that doesn't give us an equilibrium. Okay, we could have, we've exhausted all of the possibilities with y equals 0, so what about with x equals minus 3 and x equals 1? That's a contradiction. Okay, and what about with x equals minus 3 and y equals 2? Oh, that's fine. So that gives us a solution negative 3, 2. So we get two equilibria here. Now, it would be very tempting to say, oh, well, what if I take y equals 0 and x equals negative 3? That'll give us negative 3, 0. Is that an equilibrium? This is not an equilibrium, right? Because that would be, well, y equals 0 means that you satisfy the first equation. X equals negative 3 means you also satisfy the first equation. The second equation won't work out. It would be what? We would have negative 4 times negative 2 is 8, not 0. You wouldn't get a simultaneous solution. So you always had to take one condition from the first equation together with one condition from the second equation. Then you get yourself equilibria. So in this case, we have two equilibria, 1, 0, and negative 3, 2. All right, let's try one more example, a little bit more complicated. We're going to go back to our competing species model that we also talked about in the last lecture. I'm going to put in some specific numbers, though, this time. And instead of calling them P1 and P2, I'm going to call them X and Y. That's going to be a theme. It's just easier to work with them that way. We don't need those subscripts if we're only dealing with 2x2 systems. Okay, so here are our competing species. X prime equals X times 1 minus 1/2 X minus Y. And Y prime equals Y times 1 minus X minus 1/2 Y. We need to, if we're finding equilibria, we need to set these two equations equal to 0. So from the first one, we have x times 1 minus 1/2 x minus y equals 0, which gives us x equals 0, or 1 minus 1/2 x minus y equals 0, or we could rewrite that as y equals minus 1/2 x plus 1. So one of those things has to happen. And we also have y times 1 minus x minus 1/2 y equals 0. So that means y equals 0. Or, let's see, this would be 1 minus x minus 1/2 y equals 0, which is the same as 1/2 y equals 1 minus x, so y equals 2 minus 2x. Okay, so two conditions that could satisfy the first equation and two conditions that could satisfy the second equation. So we need to try all the different combinations of those conditions to get our equilibria. So let's begin at the beginning. So our first would be, we take x equals 0 from the first one and y equals 0 from the second. Great, we get an equilibrium 0, 0. All right, second, we could have x equals 0 from the first one and y equals 2 minus 2x from the second one. Is that a contradiction? Well, no, because y could equal 2 minus 2x. As long as we have x is equal to 0, that would give us y equals 2. So we get an equilibrium 0, 2. Okay, the second condition, now we have to do, we've exhausted all the possibilities with x equals 0. Our next one will be y equals minus 1/2 x plus 1 and y equals 0. Well, that's also possible. We just need to solve this equation. 0 equals minus 1/2 x plus 1. And that means that x is equal to 2. So we get the equilibrium 2, 0. All right. And then finally, we have the slightly more complicated set of conditions where we have our fourth condition is that y is equal to negative 1/2 x plus 1 and y is equal to 2 minus 2x. Is that possible? Well, yes, these are two linear equations. We're just looking for the intersection of them. Do these two lines intersect each other? And since they have different slopes, they must intersect each other. So we should be able to find a fourth equilibrium. Substituting one thing into the other, 2 minus 2x equals minus 1/2 x plus 1. So let's see, 3/2 x equals 1. So x is equal to 2/3. And plugging that into one of these equations, y is equal to 2 minus 2x. So that's equal to also 2/3. So we get an equilibrium 2/3, 2/3. All right, so it's an algebra problem, but should be a pretty easily solvable algebra problem in most cases. You just have to do some good bookkeeping, make sure you don't lose any possible combinations of conditions from the two equations that you have, or it could be more equations, and make sure that you are always taking at least one condition from each equation, not taking two conditions from the same equation. That will give you some false equilibria. You want the real things. So in this case, 1, 2, 3, 4.